or it's the probability of A plus the probability of B, but then we have to subtract the probability of A and B. And we do need this formula for problems. Some problems you could do it several ways, like this problem, but there are times where we have to know this formula. All right, let's see, is there any other problems? I think that's it for that section. All right, so that's C. And then Thursday's lesson, I guess I could call this, it's really out of the book. I'll just call it C3, but it's just a supplementary activity. And that has to do with circular permutations. All right. Now, permutations, just trying to see where we're going to learn that. All right. Permutations are where order matters. And this would be a group arranged in a certain order, but since it's a circular one, so it needs to be in a circle. So a circular permutation would be a group arranged in a circle in a specific order. So, for example, let's say we want to arrange six CDs on a tray. All right, kind of an old question here. Now, the formula we use for circular permutations is, I'll just put it up here, n minus 1 factorial, where n represents the number of trials or number needed, so in this case 6. The minus 1 comes in because it's circular. So we have 6 CDs in a tray. Let me just draw this out. A, B, C, D, E, and F. Now, if I twisted or turned this like one spot to the left or one spot clockwise or counterclockwise, they're still in the same order, even though whatever F looks like it's at the top now. So basically, this is the same as this. Oops. Yeah, there we go. So that's why we subtract 1. Maybe before we do the circular permutation, I should have maybe talked about permutation. This is something you should have done in algebra or geometry, but permutation, the formula is just n factorial. So if I have, say, four people in a line, how many ways to arrange 4 people in a line, a straight line? That would just be 4 factorial, which is 4 times 3 times 2 times 1, which is 24. But if they're in a circle, then we subtract 1 because, like I said, turning it clockwise or counterclockwise, you still got the same thing. So if it's not a circle, it's n factorial. If they are in a circle, it's n minus 1 factorial. And if you want the factorial key, so like say 4 factorial, that would be, you hit 4, math, go to probability, and factorial is the 4. So 4 factorial is 24. In the CD problem, since they are in a circular tray, it's not 6 factorial, but it's 6 minus 1 factorial, which is 5 factorial. So again, you could just figure that out the same way. 5 factorial would be 120. So if it's in a circle, we subtract 1 from that number. Now here's where it gets a little confusing. So circular permutations, we subtract 1 unless there's a fixed point. Sometimes books will call it a clasp. Then it's back to n factorial. So circular permutations is n minus 1, but if it has a clasp or a fixed point, it's back to n factorial, which is what it would be if it's just a straight line. So for example, let's say you have 4 people with a baby at the front of the table. So again, there's 4 other people and the baby. So there's technically 5 people altogether, but 4 people with a baby at the front of the table. I'm sorry, there are 4 altogether. So there's 3 people with the baby. So let's say there's baby, here's mom, here's the sister, and here's dad. All right. Now if the baby is at the front of the table. So if I rotate the other 3 people, put like dad over here, mom here, and the sister there, that is now different. These are not the same. These are different. So rotating them one spot clockwise or counterclockwise is different because we have a fixed point there. So hopefully you see the difference between the CD, where shifting it, everything shifted, but here you have at least one stationary thing, so it is a different order. All right, so now the baby's between the sister and the dad as opposed to the dad and the mother. So when it's with a fixed point, then it's just n factorial. All right, so this problem here would not be the 3 people here that are moving. We don't count the fixed point, but the 3 people that can vary their spot, it wouldn't be 3 minus 1 factorial, but it's just 3 factorial, which is 6. Whereas if the baby could move also, all right, then you get a different answer there. I'm sorry, that would be 4 factorial, which is 24. If the baby could move with that, then it would be the minus 1. All right, so there's that. Then the last thing here is we got a reflection, which is an arrangement that can be seen from 2 different views. Without changing the arrangement. All right, I got to go back to this one. This one, I was right the first time. There are 3 things that are moving. So it's 3 factorial. If the baby wasn't there, like if it was just dad, mom, and sister, then it would be 3 minus 1 factorial. So I apologize for that. So this is 3 factorial because we have 3 things with a fixed point, so it's n factorial. Where this example here, we have 3 things with no fixed point, then it's 3 minus 1 factorial, which is 2 factorial, which is not 4. That's equal to 2. A little rusty today, I guess. All right. All right, last thing, reflection. So that's something that can be seen from 2 different points of view. For example, holding a set of car keys or whatever, any kind of keys, something that's on a ring. Could be a bracelet, could be a necklace, could be a key ring. If I asked which key is on the right, you would probably say this one right here. But by flipping it here, now the other key is on the right. But I didn't change the order. It's still the same thing. They're all in the same spot. But if you look at it from above or from below or left to right, you have a different perspective. So usually what I like to say is things that you can hold are a reflection, but also like if you go to an arena, like watch a Bucks game or something like that, that would also be an example of a reflection, a graduation, where everything's in the middle. So those are reflections. But most of the time they usually use necklace, bracelet, key ring. So I always like to say something that you can hold. So we got 2 different perspectives where you can't get underneath a tray, you can't get underneath the table and lift it up. So, but this we can get 2 different perspectives from. All right, so when you have that, then since it's a circle, it is n minus 1. But since it's a reflection, we're going to divide by 2. So for example, 3 keys in a ring, there's only one way to do this. All right, so I could take off whatever, one of these keys and put them and put it wherever you want. It's still going to be the same thing. I could put it here. It's still between the smaller key and the bigger key. So I didn't change anything. So it might look like I did, but that's still, there's only one case here. So it's 3 minus 1 factorial, which is 2 factorial. 2 factorial divided by 2 is 1. There's only one way to put 3 keys on a key ring. You can try, but there's no other way. But when you put a clasp on there, last example, all right, so this was 3 keys on a ring. So that was 3 minus 1 factorial divided by 2. But now, last question, let's go 3 keys with a clasp or a fixed point. So now let's take this and call this our fixed point. This is a little hard for me to put on here. All right. So here's my clasp with a fixed point. Now if I move this key on the other side of it, now the fixed point is next to the smaller key. All right, so there are going to be more than one answer here. All right, so I guess I could show that. So right now, the little key is not touching the fixed point. But if I guess technically I'm moving this. Let me take this one off. If I move this key, to here, Now it is touching, the small key is touching the fixed point. So the answer is not 1 here. So again, with a clasp, we do not subtract 1. So the formula is n factorial. I guess I don't need parentheses up there. But since it's still a reflection, right, this is still a reflection. I can see it from 2 different perspectives. We're still going to divide by 2. So you don't subtract 1 because it has a clasp, but we still divide by 2 because it is a reflection. So circles make us subtract 1 unless it has a clasp. Reflections make you divide by 2 because you can see it from 2 perspectives. So this problem, 3 keys, so kind of like the baby, this is exactly like the baby problem, except the reflection part. Here's your baby and here's your 3 other people. These are the only ones that are moving, so we wouldn't say this is 4 factorial, we would just say it's 3 factorial. So 3 factorial divided by 2. And 3 factorial without a calculator, you could do it this way, and then the 2's cancel out and the answer is 3. We could punch it in the calculator too, but basically 6 divided by 2 is 3. So that's Thursday's lesson. Again, I didn't have any homework for that. This is more supplemental, maybe not so much IB, but more ACT. And then Friday, we will have a quiz. Again, you may want to freeze the video to get that. Let's make sure I got the whole thing on there. Okay, there's the quiz. And then here are the answers to the quiz. And you can freeze that if you need to see it a little bit more. I think I got all of it on there. All right, so that's week 4. Hopefully it's not sideways.